Hello. It's been a couple days since I've posted lectures. I've been dealing with some personal matters that prevented me from recording. Let's continue talking about group theory with some hands-on examples of working with the order of a group element. So today I want to talk about yet another group. My group is going to consist of 2 by 2 matrices. So my M is equal to the matrix A, B, C, D. All of the entries in this matrix need to be integers. So A is an integer, B is an integer, C is an integer, and D is an integer. And they need to satisfy a condition that the determinant of this matrix is equal to 1. And if you need refreshing, I'll remind you that the determinant formula is AD minus BC. So I just need 4 integers in a box, and A times D minus B times C equals 1. Those will be the elements of my group. So this group has a couple different names. This is actually one that I use in my own research, so it's one that I use a lot. I call this the modular group. Some other people might call this SL2Z. Don't worry about that. I'll just use the letter gamma to be the name of this set. So gamma consists of all matrices, which are 2 by 2 matrices with integer entries and determinant equal to 1. And if you multiply any two matrices in this set together, of course I'm talking about matrix multiplication, then you'll get another 2 by 2 matrix with integer coefficients and determinant 1. So our group operation for the modular group gamma is matrix multiplication, and our identity element for this group is the identity matrix, which is the 2 by 2 matrix I equals 1, 0, 0, 1. Now, for all of my calculations, I'll be going through the steps of the matrix multiplication, so it's okay if that's not the most familiar thing. But I want to explore how this group operates and look at the orders of two particular elements of gamma. So if I'm looking for a group, I need to have inverse elements. That's a fairly easy thing when we're doing addition, right? We just throw on some minus signs. But since we're working in matrix multiplication, right, I need to have inverse matrices. And I'll just go ahead and tell you the formula for the inverse of a 2 by 2 matrix, at least for matrices in the modular group. If I take a matrix A, B, C, D, and I want its inverse, the inverse has coordinates D minus B minus C and A. Those are the 4 coordinates for the inverse matrix, and you can check already that these are all integers. You can check that now dA minus B times minus C. Well, that's just a rearrangement of the previous formula, so we know this has determinant 1. And if you multiply this onto the matrix A, B, C, D, then we will get the identity. I'm not going to prove that. This is just a formula you can write down and remember. I won't be quizzing on matrix multiplication, though. This is just for keeping handy. Now there's two particular elements I want to look at in the modular group. I will call them S and T, and these are actually pretty important matrices for the stuff that I do. I'll talk a little bit more about that at the end of today's lecture. All we need to know right now is that S is the matrix 0, minus 1, minus 1, 0. Okay, so those are the coordinates for S. T is the matrix 1, 1, 0, 1. Right, those are the coordinates for T. And both of these matrices belong to the group gamma. Both of these matrices have an order. So I defined this at our previous lecture. The order of any group element is the smallest positive integer n, so that n copies of the element will give us the identity element, if that's possible, right? If I can find some n to make that work, then that n is going to be my smallest solution, is going to give me the order of this element. So I'm starting with S here. And if I can't find a solution to this problem, then my order of my element will be infinity, right? So I'm using some very generic language here because I don't know if the group I'm looking at, maybe it's a group with addition, maybe it's a group with multiplication, maybe it's some other weird operation, some kind of geometric formula or combining functions together. In general, we're just asking that the element, take it n times with itself, you get back to the identity, right? For us, in the modular group, we're looking at multiplication. So I can be more specific for finding the order of the matrix S. I want the nth power of S. Remember, we're using multiplication. I want the nth power of S to equal the identity matrix with coordinates 1, 0, 0, 1. Okay, so here is what I'm going to do to calculate the order of this matrix. Here I've copied the coordinates of S. S has coordinates 0, -1, and -1, 0. And I want to check that S is not the identity matrix, right? So this I, that's a pronoun, that's me, and this I is the identity matrix 1, 0, 0, 1. Is this matrix the identity matrix? No, it is not. It has completely different coordinates, so we don't have to worry about that. What does it mean that S is not the identity matrix? The identity matrix is the only element of the group that has order equal to 1. So if you are not the identity matrix, your order is not 1. Okay, cool. Just get that out of the way. Step 2, I'm going to calculate S squared, right? If this was addition, I'd calculate S plus S. So I've got 2 copies of my matrix here, and I'm going to perform matrix multiplication to see what element of the group this is. I am going to walk through the formula, but you can already see over here what we get. So if I'm going to multiply row times column, right? I'll take my column here, 0, 1, multiply it onto the row 0, 1 to get the first entry here. That formula is not completely correct. This should be a 0. But the other formulas here, -1 and 0, 0 and -1, gets me this coordinate, 0 and -1, and -1 and 0 gets me this coordinate, and so on. Those all look, that is another typo there. Okay, so my formulas here and here, I have slight typos, but the answer I've got here is correct. I get coordinates 1, 0, 0, and 1, which is in fact the identity matrix. So the square of this matrix, S times S, is the identity matrix. Now I do have a solution to S to the power n gives me the identity element. So this gives me 2 equations. First off, S to the power 1 is not the identity, but S to the power 2 is the identity. So I can solve this equation. The smallest integer n that does solve the equation is 2, right? S to the power 2 gives me the identity. No smaller positive power will solve this equation. And that's what I mean when I say that the order of S equals 2. So I can figure out from here that sure, S to the power 4 would also give me the identity, right? Because I square this side, I get S to the 4. I square this side, I get identity squared, which would just be identity. I don't even need to do the matrix multiplication to figure that out. I know that the identity times anything, x, identity times x gives me x. But 2 is the smallest power that solves this equation. So the order of S is going to be 2. It has a finite order. Now, the other thing that could happen is that we could end up with a group element where this equation has no solution. So with that in mind, let's look at the matrix T. So T has coordinates 1, 1, 0, 1. And first off, I'm going to check, is this the identity matrix? No, it is not. The identity matrix has a 0 in its top right coordinate. So my matrix T is not the identity, which means that my matrix T does not have order equal to 1. It's got to have some greater order. So just like before, I'm going to calculate T squared. So I line up my two matrices here. This time, I take my row times my column, right? 1 times 1 plus 1 times 0 gets me 1. 1 times 0 plus 0 times 1 gets me 0. 1 times 1 plus 1 times 1 gets me 2. Ooh, that's not looking good. And then 1 times 1 times 0, 1 times 1. Here gives me my 1. So T squared has coordinates 1, 2, 0, and 1. Wow, I got all the formulas correct. But that's not the identity matrix. So T squared is not the identity, which is fine. Let's keep going. What is T cubed instead? So my T cubed, I'll say I've got a T squared here, and I multiply by another T, right? I know these coordinates from the previous slide, just 1, 2, 0, and 1. And I'm going to multiply these together again, right? So still row times column. I work through the formulas and I get coordinates 1, 3, 0, 1, right? So T cubed is 1, 3, 0, 1. That's a 2 by 2 matrix. And that is still not the identity. I'm supposed to get a 0 up there. So we could go a bit further and conjecture, hey, well, this exponent up here, my T cubed, ended up being in the top right entry. Maybe that's a pattern that keeps on going? Gosh, how would I prove that? Maybe something that starts with in and ends with duction. But for right now, let's just go ahead and say that T to the power n is the matrix 1, n, 0, and 1. That is a fact. But that's a problem because this matrix T to the power n will never be the identity, right? First coordinate looks good. Second coordinate, not so good, right? This is supposed to be a 0 to make the identity matrix 1, 0, 0, 1. So T to the power n equals identity matrix has no solutions. There is no integer n I can put in there to make this equation work. So that is the situation where I'll say that the order of T is infinity. So an element with infinite order means that no finite combination of T's, in this case, will give me the identity element of my group. And this is something we can do in any possible group. You just start with whatever element you want to look at, right? Maybe we take the integers mod 7, right? That's a group. And we can take an element. I'll take 2. 2 is a residue mod 7. And to figure out the order of that element, I just keep combining it with itself. So for my example here, 2 and 2 is 4. 4 and 2 is 6. 6 and 2 is 8, which is 1 mod 7. 1 and 2 is 3. 3 and 2 is 5. 5 and 2 is 7, which is the same as 0 mod 7. And 0 is our identity element, right? So I pick whatever element I want to look at, and I try to see if some finite combination of that element with itself ever gets me back to the identity element in the group I am working with. And I really do hope that this example helps out with the quiz that I posted this week. If not, please feel free to email me with any other questions or post to our Moodle forum. Okay, I will be back in just a bit.